Section 1 Introduction. We're here to discuss the growing importance of self-supervised representation learning in pre-training vision backbones. The idea is to use large, unlabeled datasets as an extra source of training data to enhance the performance of subsequent networks and reduce the need for large labeled target datasets. Recent studies have demonstrated that self-supervised pre-training on ImageNet can rival, and sometimes even surpass, supervised pre-training, particularly in tasks like pixel-wise semantic and instance segmentation. One popular method in self-supervised representation learning involves contrastive learning. Here, the target backbone is trained to bring transformed views of an image closer in latent space than images randomly selected from the dataset. This approach has been improved by introducing spatial losses and enhancing training stability with fewer or no negative examples. Another approach involves using reconstruction losses for supervision. In this method, certain areas of an input image are hidden, and backbones are trained to reconstruct them, a process known as masked image modeling, MIM. This task is usually treated as deterministic, meaning it supervises a single explanation for the hidden region. This approach often explores masking strategies, architecture design, and training recipes to train better backbones. These methods have achieved top-tier performance when applied to vision transformer-based backbones. However, recent studies have shown that sparse CNN-based image backbones can perform just as well. In this paper, we advocate for the use of generative models as representation learners due to their simple objective, to generate data, and their intuitive representational power, which is demonstrated by their ability to generate high-quality samples, indicating they have learned semantically capable internal representations. The idea of using generative networks as representation learners isn't new. Dataset GAN and its variants proposed adding task-dependent heads on top of styligans or a diffusion model's features. These augmented networks were then used as generators of labeled data, which were used to train downstream networks. Semantic GAN, on the other hand, used style GAN with an additional task decoder as the task network itself. We present DreamTeacher, a representation learning framework that uses generative models for pre-training downstream perception models via distillation. We explore two types of distillation: feature distillation, where we propose methods for distilling generative features to target backbones without needing any labels, and label distillation, where we use task heads on top of generative networks to distill knowledge from a labeled dataset onto target backbones in a semi-supervised manner. Our focus is on diffusion models and GANs as the choice of generative models, and CNNs as the target backbones. We chose CNNs for two main reasons. They have been shown to achieve top-tier representation learning performance for both contrastive and MIM approaches, and most top-tier generative models today, GANs and diffusion models, primarily still use CNNs internally. We also experimented with vision transformer backbones, but found it challenging to distill features from CNN-based generative models into vision transformers. Generative models built with vision transformer architectures are still in their early stages, so we plan to explore DreamTeacher with these architectures in future work. Our experiments show that DreamTeacher outperforms existing self-supervised learning approaches on various benchmarks and settings. Most notably, when pre-trained on ImageNet without any labels, our method significantly outperforms methods that are pre-trained on ImageNet with full supervision on several dense prediction benchmarks and tasks. On datasets focused on objects with millions of unlabeled images, our method, when trained solely on the target domain, significantly outperforms variants that are pre-trained on ImageNet with label supervision, achieving new top-tier results. These results underscore the power of generative models, especially diffusion-based generative models, as effective representation learners that can effectively leverage diverse and labeled datasets at scale. Section Summary. Self-supervised representation learning is a popular method for pre-training vision backbones by leveraging large unlabeled datasets to improve downstream network performance. This paper introduces DreamTeacher, a framework that uses generative models for pre-training perception models through distillation. The authors experimentally demonstrate that DreamTeacher outperforms existing self-supervised learning approaches on various benchmarks, achieving state-of-the-art results on tasks such as semantic segmentation and instance segmentation. Section 2 Related Work. We'll begin by discussing the related work in the field of discriminative representation learning. Initially, these learning methods depended on manually created pretext tasks such as predicting relative patches, solving jigsaw puzzles, colorization, and relative rotation. However, our approach is different. We predict the features of a pre-trained generative model, which is trained with a straightforward and natural goal, to maximize the likelihood of the image data. The ability to create and manipulate high-quality samples is a promising indication that generative networks are learning both semantic and geometric knowledge internally. Recent advancements have been made through contrastive representation learning methods. SIM-CLR was the first to show competitive results in linear probing and transfer learning without using class labels, compared to supervised pre-training. Subsequent works like MoCo v2, and BIAL improved upon the Siamese network design by incorporating a memory bank and gradient stopping. However, these methods heavily rely on data augmentation and heuristics to select negative examples, which may not be applicable to datasets beyond well-curated object-centric ones like ImageNet. Another line of work focuses on improving the global contrastive objective and emphasizes region-based features, which are useful for dense prediction tasks. For instance, DenseCL extends MoCo v2 to predict auxiliary dense features. PixPro extends BIAL to have pixel-wise consistency across two views, while DetCon introduces masked pooling to focus on object-wise features. However, these methods require special designs for certain tasks or additional heuristics for complex scene datasets. In our work, we focus on generative networks for representation learning, specifically for various dense prediction tasks. Moving on to generative representation learning, the concept of using generative models for learning representations for recognition tasks has been around since Hinton's time. Recent works have used advanced generative models and techniques to develop representation learning methods. For example, BigAN proposed to jointly train an encoder with an adversarial training objective. BigAN used the advancements of BigGAN and showed competitive linear probing results in ImageNet. Methods like IGPT and VIM pre-train large transformer networks with autoregressive generative pre-training objectives, achieving compelling linear probing results on ImageNet. However, they did not show results on dense prediction tasks. Moreover, these methods train a single image backbone with both discriminative and generative objectives and thus cannot leverage the specific designs for each. Dataset GAN was among the first to show that a pre-trained GAN can significantly benefit perception tasks, especially in the low-labeled data regime. Specifically, the authors added a task-specific head on top of style GAN and synthesized a labeled dataset for training downstream perception networks. Semantic GAN proposed to model the joint distribution of images and labels. Inference was performed by first encoding the test images into the latent space of style GAN and then decoded the labels using the task head. DDPM-SEG followed this line of work but used a denoising diffusion probabilistic model, DDPMs, instead of style GAN. In our paper, we continue this line of work but focus on distilling knowledge from a pre-trained generative model, specifically a diffusion model, to downstream image backbones as a general way of pre-training. We provide an extensive evaluation of generative networks in the context of representation learning on various benchmarks and tasks. Lastly, we'll discuss knowledge distillation. Hinton and his team were the first to propose knowledge distillation as an effective way to improve performance. The idea was to distill logits from a large teacher network into a smaller student network. FitNets proposed to mimic the teacher's intermediate feature activations as additional hints for the student network. Subsequent works tried to utilize different forms of knowledge from the teacher network, spatially, channel-wise, and from multi-levels. Usually, the teacher and student networks share a similar training objective, the network architecture, and require labels to train the teacher network. In our work, our generative model is treated as a teacher and is trained without labels, and the objective is not task-specific. Our student networks are image backbones of choice, which might not share a similar architecture as the teacher. Section summary. In the related work, previous methods for representation learning relied on handcrafted pretext tasks or contrastive representation learning. Some methods focused on generative representation learning, leveraging generative models for recognition tasks. Knowledge distillation has also been used to improve performance by transferring knowledge from a large teacher network to a smaller student network. In this paper, the authors propose distilling knowledge from a pre-trained generative model to downstream image backbones as a general way of pre-training, without requiring labels or a task-specific objective. Section 3 DreamTeacher Framework. We're going to explain our DreamTeacher framework, which we've used in two different scenarios. One where we don't have any labels during the pre-training phase, known as unsupervised representation learning, and another where we have some labels available, known as semi-supervised learning. In both cases, we use a trained generative model, denoted as G, and we aim to distill its learned representation into a target image backbone, denoted as F. The first step is to create a feature dataset, denoted as D, which consists of images and their corresponding features extracted from the generative model. Then, we train the image backbone using this dataset by distilling the features from the generative model into the intermediate features of the image backbone. We mainly focus on convolutional backbones, leaving the exploration of transformers for future work. In the case of unsupervised representation learning, we attach feature regressors at different levels of the image backbone to regress the corresponding generative features from an image. We first discuss how to create a feature dataset, then we explain the design of feature regressors, and finally, we introduce our distillation objective. There are two ways to create our desired feature dataset. One way is to sample images from the generative model and record intermediate features from the generative process. This could potentially create datasets of infinite size, but it might suffer from issues such as mode dropping, where the generative model may not have learned some parts of the distribution sufficiently well. We call this a synthesized dataset. The other way is to encode real images, whether they're labeled or not, into the latent space of the generative model using an encoding process. We call this an encoded dataset. A synthesized dataset is created by sampling images from the generative model's prior distribution. We record hierarchical intermediate features from this process. We use this approach when using generative adversarial networks, GANs, as our generative model, due to their fast sampling speed and inability to encode real images by design. An encoded dataset, on the other hand, is created by encoding a real image into the latent space of the generative model using an encoding process. For generative models that come with an encoder network by design, such as variational autoencoders, VAEs, we can simply reuse it. For diffusion-based generative models, which is the class of generative models we focus our investigation on, we use the forward diffusion process to encode a real image. Both synthesized and encoded feature datasets can either be pre-computed offline or created online while training the image backbone. In practice, we use online sampling for synthesized datasets and online encoding for encoded datasets to allow fast in-memory access and efficient materialization and removal of samples and corresponding high-dimensional features. To distill generative representations into a general backbone, we design a feature regressor module that maps and aligns the image backbone's features with the generative features. Our feature regressor takes multi-level features from the backbone and uses a top-down architecture with lateral skip connections to fuse the backbone features and outputs multi-scale features. Our feature regression loss is simple and is inspired by FitNet, which proposed distilling knowledge from a teacher onto a student network by mimicking intermediate feature activations. We also explore the activation-based attention transfer, AT, objective, which distills a one-dimensional attention map per spatial feature, using an operator defined to sum the power of the absolute values of the feature activation across the channel dimension. This improves convergence speed over regressing high-dimensional features directly. Our combined feature regression loss is the sum of the mean squared error, MSE, loss and the AT loss, where the AT loss is weighted by a factor of 10.0 to make the two losses in the same scale. We empirically ablate choices of the loss function and feature regressor designs. Section summary. The DreamTeacher framework is described in two scenarios: unsupervised representation learning and semi-supervised learning. In both scenarios, a generative model is used to distill its learned representation into a target image backbone. The framework involves creating a feature dataset, training the backbone using distillation, and using feature regressors to align the backbone features with the generative features. Section 3.2 Label-Guided Representation Learning. In the context of semi-supervised learning, where we have access to some labels for pre-training, we develop a task-specific branch known as a feature interpreter. This is built on top of our existing generative network, which remains unaltered during this process. This approach is inspired by dataset GAN. Unlike dataset GAN, which creates a labeled dataset for training downstream task networks, we use a method called soft label distillation for both encoded and synthesized datasets. This means we incorporate predicted soft labels into our feature dataset. This process is illustrated in Figure D. Let's talk about the structure of the feature interpreter and our distillation goal for soft labels. The feature interpreter is designed similarly to big dataset GAN, which enhances the interpreter design of dataset GAN by improving memory efficiency and prediction accuracy. The interpreter takes multi-level features from the generator as inputs. These inputs are processed through a series of feature fusion layers, as shown in the figure, to reduce the feature dimension and combine with the next level features, ultimately producing per pixel logits. We follow big dataset GAN's interpreter design, but we replace the convolutional fused block with depth-wise separable convolutions, group norm, and swish activation. We train the interpreter branch using segmentation labels and employ a mix of cross-entropy and dice objectives for training. Here, the weights of the feature interpreter are represented by I_theta, and Y represents the task labels. The pixel-wise cross-entropy loss is denoted by H, and D represents dice loss. We use a hyperparameter, lambda_d, to balance the dice loss, and in all our experiments, we set lambda_d to 3.0. For label distillation, we use a method that involves the cross-entropy of the logits from the feature interpreter and the logit head of the target image backbone. The temperature tau controls the sharpness of the output distribution, and we set tau to 4.0 in all our experiments. We combine the labeled distillation objective with our feature distillation objective to create a mixed distillation loss. Here, lambda_LD is a hyperparameter that controls the balance between the losses, and we set lambda_LD to 1.0 in our experiments. We pre-train the image backbone using the mixed distillation losses over all images in our pre-training dataset, regardless of whether they are labeled or unlabeled. We only use annotated labels for training the feature interpreter, and we only use soft labels from the feature interpreter for pre-training with distillation. Section summary. In the semi-supervised setting, we train a task-dependent branch called a feature interpreter on top of a frozen generative network. We use soft label distillation for both encoded and synthesized datasets, and the feature interpreter takes multi-level features from the generator as inputs to output per pixel logits. We train the interpreter branch with segmentation labels using a combination of cross-entropy and dice objectives, and we use label distillation in conjunction with feature distillation for pre-training the image backbone. Section 4 Experiments. In this section, we'll discuss the experiments we conducted to evaluate the performance of our model, DreamTeacher. We tested it in two scenarios: self-supervised representation learning and semi-supervised learning. We also examined how well our model performs when the same dataset is used for both pre-training and fine-tuning, a process we refer to as in-domain pre-training. We also explored the impact of different generative models and design choices on the performance of DreamTeacher. We tested several generative models, including BigGAN, ICGAN, StyleGAN2, ADM, and Stable Diffusion models. We used 4 datasets for pre-training: BDD100K, ImageNet-1K, LSUN, and FFHQ, which contain 100,000, 1.28 million, 10 million, and 100,000 images, respectively. Our focus was on convolutional networks as the target image backbones. We first validated the effectiveness of DreamTeacher for ImageNet pre-training. We followed the recent state-of-the-art method, Spark, and evaluated 2 convolutional architectures, ConvNextB and ResNet50. We pre-trained image backbones unsupervised on ImageNet-1K. For comparison with transformer-based self-supervised methods, we pre-trained a modern CNN-based backbone ConvNext with a similar number of parameters. We also pre-trained and evaluated a classical backbone, ResNet50, to ensure a fair comparison with CNN-based self-supervised methods. We used a pre-trained unconditional admiral with a resolution of 256. We only used horizontal flip augmentation and trained using the LAM optimizer with a batch size of 2048. We adopted a cosine annealing learning rate with a peak value of 0.0002 times the batch size divided by 256. We then assessed the quality of the learned representations by fine-tuning the pre-trained backbone with additional heads per task. We tested the performance for ImageNet classification and COCO instance segmentation, which are representative global and spatial image understanding tasks. Our model, DreamTeacher, outperformed existing approaches in both detection and segmentation, and performed on par in the classification setting. Specifically, DreamTeacher achieved 52.5 and 45.2 average precision on the COCO instance segmentation task, outperforming the state-of-the-art transformer-based method IBOT. DreamTeacher also outperformed the recently proposed sparse convolution-based MIM method Spark in the tasks of detection and segmentation. However, our method did not outperform this baseline on the task of image classification. This could be due to our approach of distilling spatial features from the generative model, which might contain more semantically localized information for generation. It's also worth noting that our method is about 2.5 times more efficient than Spark in terms of effective training epochs on ImageNet. This number includes training steps of the generative model, Admiral. In another experiment, we evaluated ImageNet classification performance with full fine-tuning and COCO instance segmentation with 2 schedules. We achieved comparable performance as baselines for ImageNet classification. For COCO instance segmentation, we notably outperformed all contrastive methods and the masking-based approach Spark. We further evaluated transfer learning on the AID20K semantic segmentation task and BDD100K instance segmentation task. Our approach using generation as pre-training task outperformed both global and dense contrastive pre-training tasks as well as the masked image modeling task. Section summary. In this section, the authors evaluate the performance of DreamTeacher in self-supervised representation learning, semi-supervised learning, and in-domain pre-training. They experiment with different generative models and design choices, using 4 datasets for pre-training. The results show that DreamTeacher outperforms existing approaches in detection and segmentation tasks, but performs on par in the classification setting. The method is also more efficient than the Spark method in terms of training epochs on ImageNet. Section 4.2 In-Domain Pre-Training. In this section, we'll discuss our approach to in-domain pre-training. We start by pre-training the main model using various self-supervised training methods. We then assess the effectiveness of this pre-training by fine-tuning the model on different tasks, using label supervision, all within the same dataset. It's important to note that both our baseline models and our DreamTeacher model use randomly initialized downstream models. We test our unsupervised pre-training using the BDD100K benchmark and semi-supervised pre-training using multiple datasets from the label efficiency benchmark. For the BDD100K benchmark, we pre-train all self-supervised learning methods, including DreamTeacher, on 70,000 in-labeled images from BDD100K. We then evaluate all methods on BDD100K, which contains 10,000 images annotated with semantic, instance, and panoptic labels. We use 7,000 labels for supervised training, following the official dataset split. The results are reported on the validation set, which consists of 1,000 images. For all methods, we use a RESNET50 model. We also visualize the knowledge learned by different generative models. Specifically, we show scenes sampled from StyleGAN2 trained on BDD100K. We perform K-means clustering of StyleGAN's features and visualize clusters with different colors. The clusters roughly correspond to major semantic classes. In our results, we compare DreamTeacher with the representative contrastive method BILE and the recently proposed MIM-based method Spark on the BDD100K instance segmentation task. We found that contrastive and masking-based self-supervised methods require a longer pre-training schedule to converge on a small in-domain dataset. We pre-trained models using DreamTeacher feature distillation with StyleGAN2 and ADM, and the effective epochs comprise 300 training epochs of the generative model and 600 training epochs for feature distillation. Our methods significantly outperform contrastive and masking-based techniques for in-domain pre-training with better training efficiency. Notably, our method with Admiral outperforms the ImageNet supervised pre-trained model, showing promising results without relying on large-scale curated datasets like ImageNet. Next, we evaluate in-domain pre-training in our semi-supervised setting. We train on bedroom, cat, and horse categories from LSUN, and human faces from FFHQ, at 256 by 256 resolution. We evaluate semantic segmentation, where the datasets have 28, 15, 21, 34 semantic classes, respectively. Datasets contain only 40, 30, 30, and 20 labeled images. We pre-train all models from scratch, without ImageNet pre-trained initialization. We use U per net for semantic segmentation. We found that given the same model, ResNet 101, DreamTeacher trained with our mixed distillation outperforms dataset DDPM across all datasets. We outperform dataset DDPM by 3.4% on FFHQ34 and 9.1% on CAT15. Using both a 10x and a 6x smaller model, RESNET101 and a ConvNXB, respectively, we outperform DDPM seg on all classes. On Bedroom 28 and Cat 15, we improve over the baseline by more than 5%. Given the same model, our method significantly outperforms pre-training with ImageNet classification labels. With ConvNXB, our proposed approach is better than ImageNet pre-training by more than 10% on Bedroom 28, Cat 15, and Horse 21. These results suggest that if the in-domain datasets are sufficiently large relative to the complexity of the task, in-domain pre-training is more effective than pre-training on large generic datasets like ImageNet. This holds true for both semi-supervised and unsupervised pre-training. Section Summary. In this section, the authors discuss their in-domain pre-training approach, where they pre-train the backbone using self-supervised training methods and evaluate its efficacy by fine-tuning on different tasks with label supervision. They evaluate their methods on the BDD100K benchmark and multiple datasets from the label efficiency benchmark. The results show that their approach outperforms contrastive and masking-based techniques for in-domain pre-training, even surpassing ImageNet pre-training without relying on large-scale curated datasets. Section 4.3 Ablation Studies. In Section 4.3, we conduct a series of ablation studies. Initially, we test DreamTeacher with various generative models as shown in the table. The results indicate that the Admiral model, trained on the Indiana 1K to 1M dataset, delivers the highest performance in downstream tasks. We also experimented with the readily available Stable Diffusion model, trained on the LAION 400M dataset, and pre-trained the backbone on the Indiana 1K to 1M dataset. However, this setup didn't perform as well as the Admiral model trained on the Indiana 1K to 1M dataset. In the table, we also examine the impact of our proposed distillation losses. We found that a combination of feature and label distillation provides the best results, with the exception of the FFHQ34 dataset. We also present our decisions regarding the decoder used in pre-training, loss functions, encoding modes, either deterministic or stochastic, and the number of diffusion steps in the respective tables. For these ablation studies, we pre-train the backbone for 100 epochs and evaluate its performance on the BDD 100K instance segmentation. The results validate our choices. However, our framework does have some limitations. It depends on generative models for representation learning, and training these models on large-scale, high-resolution datasets can be expensive, particularly with diffusion-based models. Moreover, our feature distillation method only takes into account features at the same spatial resolution, and we restrict our focus to CNN-based image backbones. The task of distilling features into vision transformers is something we plan to explore in future work. Section Summary. In this section, the authors conducted ablation studies to evaluate different generative models and distillation losses in their proposed framework. They found that the Admiral trained on Indiana 1K to 1M achieved the highest downstream performance. They also explored the use of off-the-shelf stable diffusion trained on LAION 400M but found that it performed slightly worse. The authors further analyzed their design choices for the decoder, loss functions, encoding modes, and diffusion steps, and confirmed their effectiveness through pre-training and performance evaluation on the BDD 100K instance segmentation dataset. However, the framework has limitations in terms of the cost of training generative models on large-scale datasets and the restriction to CNN-based image backbones, with future work focusing on distilling features into vision transformers.